Rate laws. So now let's talk about rate laws. So chemical reactions are reversible, and in our previous discussion of the decomposition of nitrogen dioxide, we have so far considered only the forward reaction, which is as shown here. So the reverse reaction can also occur, but to avoid any form of complications that may occur under conditions where the reaction is reversible, we simply assume that the contribution from the reverse reaction is negligible. That is, we are studying the reaction soon after the reactants are mixed or before the products have had enough time to build up to significant levels. So this is the forward reaction, and let's say this is the rate expression here. So such an expression that shows how the rate of a reaction depends on the concentration of the reactant in such a rate law. So this is a rate law, and the K here is the rate constant, or simply called proportionality constant. So N is the order of the reaction and must be determined by experiment. So the order of the reaction can be an integer. So it can also be a fraction, and it can even be zero. So it is important to note this, that the concentration of the products. So this, looking at this equation here, so the concentrations of the products do not appear in the rate law because the reaction is being studied under conditions where the reverse reaction does not contribute to the overall reaction. Another important note is that the value of the exponent here must be determined by experiment. So it cannot be written from the balance equation. That is to say, we cannot just say that because the coefficient of the reactant here is 2, and just say that rate equals to K n over 2 plus power 2. So this is wrong. So it has to be determined experimentally. So now let's talk about the types of rate laws. So we have the differential rate law and the integrated rate law. So the differential rate law expresses how the rate of a reaction depends on the concentration. So for example, given the equation here, we have the decomposition of nitrogen dioxide again. So we have this where everything is gas. So we have gas. So to write a differential rate law for this, we can simply say that the rate equals -1/2 the change in nitrogen dioxide over change in time equals +1/2 changing this over the t, and we have +1/1 change in concentration of oxygen over change in time. So we might also write this as rate equals -1/2 change in nitrogen dioxide over the T to give K equals to N to 2 raised to power N. So we can also write it, we can either write it in this form or in this form. So let's say we have the reaction XA plus YB to give the products. So to write the differential rate law for this equation, we can simply write that rate equals -1/x, the A over the T equals -1/y, the B over the T. So we can also write it that, so we have all rate equals -1/y, the B over the T equals K A N, and we have B. So the overall order of the reaction is overall order equals to N plus N. So we have that. So integrated rate law expresses how the concentration, these are the concentrations. So integrated rate law expresses how the concentration depends on time. So it includes first order, it includes the second order, zero order, and all of that. So we shall consider that in details in later videos.